Hello, check. Alright, people. I believe we are finally live. I will use this mic as a handheld mic once again because all the mics in the entire Vedantu building are bad. So I'm in an entirely different studio, so I had to set up the camera and everything. So people just let me know if the focus is fine. I've put it to autofocus, and sometimes autofocus is weird, but yeah. If that works, then I am happy. The mic the clip of the mic is totally separate from the mic, so I don't know how other teachers are managing, but I have no idea. Anyway, people, welcome to Catalysis by Vedantu. My name is Pahul. If I'm audible and visible, please write here in the chat box. You know the drill. And today we are here to do the fourth lecture of the solid state chapter. And today we are going to understand something very interesting. That is three-dimensional packing. Yes, in the previous classes, we understood a lot of things. We've understood rank, we've understood density, we've understood what's a unit cell, we've understood what are the types of unit cells, we've understood Bravais lattices as well. And in today's class, we will understand how basically these three-dimensional lattices are formed. Yeah. So as I told you in the first class that in nature, you don't start with a unit cell. Unit cell is our imagination, right? We have defined a unit cell by looking at the lattice and saying, okay, this tiny little thing is the repeating unit. And then that keeps repeating, so we call it a unit cell. So that unit cell is basically an imaginary thing that we are able to observe in the entire lattice. The lattice, however, is created by nature already. And we observe in nature, there are multiple types of patterns in which these lattices are created. These lattices are created with the concept of closed packing. Okay. So what happens is, we have something called closed packing, and the most basic idea of closed packing is what we will start off the class. Okay, we'll start the class with the most basic idea of two-dimensional closed packing. Fine. Now what happens in two-dimensional closed packing is, first of all, we need to assume that all the constituents of a lattice are spheres. Okay, all the atoms or metals or ions that might be creating a solid, all of them are spheres. That's our first assumption. Okay, camera focus is weird. Okay, let me change the mode of the camera's focus. Just a second, people. यार ये रात को क्लास लेने में ना यही दिक्कतें होती हैं. I'll put it out autofocus static. Let's see what it does. So instead of continuous movement of the autofocus, I've put it at static autofocus. Maybe this is better. कोई बात नहीं यार. Dhanupriya is saying, why is it particularly spheres? Because that's the best assumption of an atom, right? I mean, you can't imagine an atom to be a cube. That'll be weird. So that's what. So we'll talk about two-dimensional closed packing first of all. So think about one dimension to start with. In one dimension, if I have to arrange spheres and I have to keep them as close as possible, how will I arrange them? Obviously, like this. You will keep them right next to each other. Yes. You will keep them right next to each other and their boundaries will be attached to each other. Yes. Cool. Got it? So this is your one-dimensional closed packing. Okay, one-dimensional closed packing. CP bolo to closed packing over here. Fine. Now, my dear friends, if I have to turn it into two dimensions, I have to basically put circles. We won't have spheres in two dimensions, obviously. So we have to put circles in the plane of the screen. Yes. So how do I put the next layer on top of it? There are multiple ways of doing it. The first way that we will do, putting the second layer on top of this first layer, is to keep the spheres on the same, or to keep the circles on top of the original circles. Okay, something like this. ठीक है जी, you get the idea? I am putting the next layer on top of the first layer. Then the next layer I'll put again on top of the spheres. Yeah. This is an arrangement that I can do. Another kind of arrangement that I can do in 2 dimensions is something that looks like this. Let's start off with the same base layer, some spheres right next to each other. Cool. And now let's keep the next layer in the gaps. Okay, let's keep the next layer in the gaps. And my drawing has started to fail me over here. Okay, forget about these. Bada bada banate. Yes. Okay. People, just give me a moment. My drawing skills are very bad. But I'll try to make things done. I'll try to get things done properly. Don't worry. You also draw this along with me in your notebook and you'll also realize it's difficult to draw. तो जी, the next layer of spheres, भाई जी ध्यान से बनाएंगे हम बहुत, ये देखिए. So what I am doing is I am keeping the next layer of spheres on the gaps of the first layer. Yeah? Can you see I am keeping the next layer of spheres on the gaps of the first layer? And the next layer, once again, I can keep on the gaps of the second layer. Yeah, I can keep the next layer in the gaps of the second layer. Something like this. Getting the idea? Yeah. Fine. Now, people, in both of these cases, notice something very different, distinctly different. Over here, can I see squares that are repeating? Can I see these squares? Yeah, all of these are squares. Fine. So this, my dear friends, is known as your 2-dimensional square packing. One very interesting way to imagine this is, let's say you want to sell oranges. Okay, let's say you want to sell oranges. Imagine, okay, close your eyes and imagine that you somehow you weren't able to crack JEE or NEET. Worst case scenario. And then you're like, I don't want to do studies, screw studies. What I want to do is I want to sell fruits. So if you want to sell fruits, then what will you do? You will purchase a cart and you will start keeping oranges on that cart. So for the first day, let's say you're keeping only 1 layer of oranges. So you can arrange that 1 layer of oranges either like this, square packing, keep all the oranges. This is the top view of your cart, basically. ठेला लगाया, ऊपर उसका top view है. People know this example from eternity. So yeah, ठीक है भाई, क्या कर सकते हैं? I don't have new examples. If you want to sell anything else that is spherical, it's your wish. If you arrange your oranges like this is the top view of your cart. Yeah, you're selling your oranges. Then this is what it looks like. Now over here, I'm sure you can see. Over here, I'm sure you can see hexagons. Can you see hexagons? Yes, people. Can you see this hexagonal unit over here as well? So you can see these hexagonal units are essentially repeating again and again. Fine. And therefore we will call this 2-dimensional hexagonal packing. Fine. This is your 2-dimensional hexagonal packing. 2-dimensional square packing, 2-dimensional hexagonal packing. Please make sure you write this down. Someone knew, yes. People, is the mic better now, by the way? Compared to that other studio? Dhanupriyan is saying, what's the use of this concept in real life, sir? So Dhanupriyan, so the thing is that this idea, to understand this, helps us understand the intricacies of solid lattices, of solid crystals. Fine. So you can do X-ray crystallography to understand the structure of solids, and then you can realize, okay, this is a certain pattern that's repeating. So this certain pattern that's repeating will help you understand a lot of properties of the solid. We will do a lot of questions related to the same as well. Okay. In real life, this is of use to you if you are studying chemistry later on in life. Or as someone new is saying, the real life use of this concept is to sell oranges and start the solid state enterprises. But you can do that if you want. So this is 2-dimensional. Now in 3 dimensions, what we can do is we can take multiple layers of, let's say, square packing, keep them on top of each other. We can take multiple layers of hexagonal packing, keep them on top of each other, right? And that will give us 3-dimensional packing. Yeah? So what you are doing basically is on your solid state enterprises orange selling stall, after a few days you gain popularity. Like, JEE fail, solid state enterprises, orange selling stall. That's your that's the name of your company. So after a few days you gather popularity. Are tu bhi fail, main bhi JEE fail. So people will come to buy more oranges from you because they are also JEE fail. So anyway, I hope none of you fail JEE. You all should crack JEE with flying colors. But example, just for the sake of fun. So you gather popularity and you want to sell more oranges now. So your space is, you don't have any more 2-dimensional space on the cart. So you'll stack up oranges, yeah? You'll make a beautiful stack of oranges, one on top of the other, nice layers and everything. And people will be like, okay, fine. You fail JEE, but you don't fail solid state. Enough of that joke. I'm not going to repeat that again. So how do we stack these things up in 2 dimensions? So people, just beautiful representations of the square packing and the hexagonal packing taken from the NCERT. If you want to look at them and realize how bad my drawing skills are, go ahead, do so. You can badmouth my drawing skills after looking at this. Pahul Sir ka drawing, modern art. Yeah. So now we'll take these 2-dimensional layers and we'll stack them on top of each other to create something like this. Everyone understands this jazz. Sabko samajh aati hai ye. What is happening over here? You've basically taken multiple square packed layers. Can you see this particular layer on top? Yeah. This layer on top, can you see? This is a square packed layer. This is a square which is represented in 3 dimensions, so it looks very nice. So when you stack squares on squares on squares, what will you get? You will get cubes. Fine, very simple. The visual is very nice to see. So now, my dear friends, in this entire thing, can you see this repeating unit that they've drawn out very nicely? And I will ruin their drawing. Can you see this repeating unit? This cube is the repeating unit. And in this cube, do you notice that the atoms, the oranges, which are basically atoms, these atoms are present at the corners. Yeah. This particular one, this guy over here, this guy over here, this guy. Yeah. This one, this one, this one, and the one hidden at the back. Do you see that all those atoms are present at the corners of this cube? So my dear friends, what is this? This is basically your simple cubic. Simple cubic unit cell. So what has happened over here is, let me give you the story once again, that nature was deciding that it wants to sell atoms. You were selling oranges, nature wants to sell atoms. So it had to arrange atoms one on top of each other. The first layer was square packed layer. The second layer also square packed layer placed right on top of the first layer. Then again square packed layer right on top of the first layer. Then square packed layer right on top of the previous layer. You keep on repeating this arrangement. You get this type of a arrangement. This type of an arrangement, solid lattice. Now in this particular lattice, the unit cell that we get, when nature does square packing in 3 dimensions like this, the unit cell that we get out of this lattice is a simple cubic unit cell. That's the entire story. So nature has different forms of packing. We are studying certain forms, square closed packing and hexagonal closed packing. We saw them in 2 dimensions. And when we extrapolate that to 3 dimensions, we get different arrangements. These arrangements are basically solid lattices. And in solid lattices, we can have the smallest repeating unit. In this case, it is the simple cubic unit cell. Someone new, yeah. AVR Pavan Kumar, interesting bro. Anyway, ठीक है दोस्तों. So now over here what I want to show you is this AAAA and ABAB. What do you mean by AAAA and ABAB? See, over here all of these layers are placed right on top of each other. This layer is the same as this layer, is the same as this layer, is the same as this layer. Therefore, all the layers have the same pattern. Let's call it pattern A. So pattern A keeps repeating, A type of packing. This particular thing can be called A, so on and so forth, type of packing. Or for the sake of simplicity, you can just call it AA type of packing. Basically A on top of A on top of A. Over here on the other hand, the first layer, the second layer is now placed on the gaps of the first layer. Yeah. Then the third layer is as good as the first layer. The fourth layer is placed on the gaps of the third layer, which makes it as good as the second layer. Yeah. Isn't it? So this can be called the AB type of packing. I'm sure you can see the difference between the first arrangement and the second arrangement. Yeah. The first arrangement, the second arrangement is just shifted a little because we want to place the second arrangement on the gaps of the first arrangement. Right? Spiritual, I am glad you're happy about the fact that I'm back. AB. So I can call this the AB type of packing. Coolio. That's it. Someone knew that's absolutely correct. We'll come to that eventually. Badhiya ji, AA type of packing, AB type of packing. This is 2 dimensions. Now in 3 dimensions. In 3 dimensions, if the base layer, okay, the entire base layer, ये जो पूरी layer है, this entire layer, if that is layer A, this entire layer that is there, the flat layer of oranges, the first layer of oranges, this is say layer A. Do you realize the other layer is also layer A? This is also layer A. This is also layer A. We're basically keeping layer A on top of layer A on top of layer A on top of layer A. So essentially this is again A type of 3D square packing. Got it? Got the entire story behind this statement? That's what we need to know. Very nice. अब चलते हैं थोड़े और interesting packing की ओर. Let's go towards a slightly more way of arranging things. Fine. Now, let's try to create a beautiful 2-dimensional packing that is hexagonal. Okay. Why am I doing this over here? One by one, because I want you to draw these things along with me. I do have an image of this later on, and I have a very beautiful video that I found on YouTube from a different channel. I'll tell you what channel it is. And that video has very beautiful 3-dimensional animation of the entire thing. So first I want you to draw this, then I will show you this in better image form, then I will show you the entire thing in video form as well. Okay, fine. So step by step. Chalo, ye ho gaya. One layer. Now the next layer for hexagonal packing, we are going to place in the gaps. Please keep drawing this in your notebooks along with me. Okay. We'll draw another layer which is as good as the first layer. So essentially you have your AB type of packing. Yes. Now my dear friends, this is one layer. You have to place another layer on top of this layer. This is the top view of your orange stall. You have to place another layer on top. Okay. Flat layer, you have to place another layer on top. Basically, now you have to place spheres on top of it. Where can I place the next layer? Where can I place the next layer is my question. All right. Vishwajit, the focus will come back. Okay. Now it's fine again, right? वो होता रहेगा. It's on autofocus mode, so when I went out of the screen, the focus got blurry. So what do we do now? We can place the next layer in these gaps. ये gaps देख रहे हो? Can you see these gaps? Can you see those gaps? So let's try to place spheres in those, on top of those particular gaps. Okay? इनके ऊपर रखने की कोशिश करते हैं. Something like this. Where are these gaps once again? Here. Yeah. These gaps, what do they look like? They basically look like this. Upward triangles. Upward pointing triangles. Yeah. Something like this you can keep. Getting the idea of what is happening? I had the base layer. Now I'm keeping the top layer on certain gaps that I can see. Fine. Badhiya. Awesome. Is there another way of doing the same thing now? The blue spheres that I've put, is there a different type of gap where I can put those? कुछ और है क्या अपने पास? Think. We can कर सकते हैं क्या? Is there a different way? Not really. Why? Because all the gaps in the first layer are basically the same type of gaps. If you are looking at the downward triangle gaps, they are also the same as the upward triangle gaps. You're just looking at the structure like this. So to place the second layer, this is the only best way. We are not doing the AAA type of packing because वो आपके oranges गिर जाएंगे और oranges will fall here and there. So we're not thinking about that. First layer is A. Then the second layer is B because the second layer, the blue layer, has been placed on the gaps of the first layer. All the gaps of the first layer are basically the same. Fine. Now the third layer placement is what makes our life interesting. The placement of the third layer is what makes our life interesting. Where can we place the third layer in this scheme of things? Where can we place the third layer of things? Now we can either place the third layer on the gaps of the blue layer, or we can place the third layer where the first layer already is. ठीक है? दोनों चीजें कर सकते हैं अपन. The third layer can be placed in these particular gaps. Let me try to get the green pen working. This board is very weird. You have to read some mantras and stuff to get it to full green. This is green. Fine. We'll work with this. So notice this particular gap. Notice this particular gap. This particular gap. Okay. This particular gap. we can place the third layer on top of these gaps now. मस्त खिचड़ी पका दिया अपन ने यहाँ पे, but I'll show you a better looking image, so don't worry. The third layer is on the gaps of the second layer now. Yeah, that's one way. Or you could have placed the third layer right on top of the first layer. Yeah, third layer right on top of the first layer. Something like that. Okay. So now this hodgepodge that we've created, let me try to show you a better image and then I'll show you a video. Okay. And in that video, things will become much more clear to us. ठीक है दोस्तों, ये अपने पास है. This is what is this O, what is this T? I'll tell you in some time, don't worry about it. So we have the first layer which is a little more faint, little more transparent, yeah. And then we have the second layer with the brighter spheres. Cool. इस तरह से कर दिया अपन ने, right? Now the next layer can be placed either in these gaps, okay, all these O gaps that are there, you can place the next layer on top of these O kind of gaps. What is this O? What is this T? We'll learn in a little while. Don't worry about that. So the next layer can be placed in these gaps, let's say. Fine. This is a way to do it. Or the next layer can be placed right on top of the first layer. Okay? We can place the next one right on top of the first layer, something like this. Too much layer हो गया ना अभी. So let me show you an animation, a video. So this is a video that I found on YouTube, okay? And it's a very nice video that they've made. Just give me a second.
Into 3 steps. Close packing of spheres in one dimension. In one dimension close packing, there is just one way of arranging the spheres. Here, the spheres are arranged in a row touching one another. As a result, each sphere is in contact with 2 neighboring spheres. Thus, in one-dimensional close packing, the coordination number is 2. Close packing of spheres in 2 dimension. Close packing structures in 2 dimension can be generated by stacking rows of one-dimensionally closed packed spheres, one above the other. This can be done in 2 ways: square close packing and hexagonal close packing. Square close packing. In this type of packing, the second row of spheres is placed in contact with first row in such a way that the spheres of the second row are placed exactly above the spheres of first row. In such an arrangement, the spheres are aligned horizontally and vertically such that each sphere is in contact with 4 other spheres. As A-type row, the second row being exactly same as the first row.
So yeah, you're basically revising the square packing that we've already done, and then it will come to the 3D packing. So just watch the entire thing, okay?
Hexagonal close packing. In this type of packing of spheres, the second row of spheres is placed in a staggered manner such that the spheres fit in the depressions of the first row. If we call the first row as A-type, then as the second row is different from the first row, it can be called as B-type. Now, if we place a third row above the second row in the similar manner, we will observe that the third row spheres are aligned with those of first layer, and each sphere is in contact with 6 other spheres. So, the coordination number is 6. Similarly, on placing the fourth layer, we will observe that the fourth row of spheres are aligned with those of second layer. Hence, this type of arrangement is known as AB-AB type of arrangement or hexagonal close packing. If we compare square close packing with hexagonal close packing, we will observe that empty spaces are less in hexagonal close packing than compared to square close packing. Now, what are these empty spaces and what role do they play in packing efficiency? The empty spaces in between the spheres are known as voids. These voids are responsible for decrease in packing efficiency of the solid crystal. More the number of voids, less is the packing efficiency of the crystal. Now, you must be wondering what is meant by packing efficiency. We have discussed about this in later part of the section. Now let us study about close packing in 3 dimension. 3-dimensional close packing from 2-dimensional square close packed layers. This type of packing is obtained by placing 2-dimensional square closed packed layer above the first one, such that the spheres of the second layer are exactly above the spheres of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally and vertically. On arranging layers one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres. 4 from the same layer, 1 from the layer above, and 1 from the layer below that sphere. So, the coordination number is 6. If we call the first layer as A-type, and since all the layers are also of the same type, this kind of arrangement is known as AAA type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cubic lattice, and its unit cell is primitive cubic unit cell. Dimensional close packing from 2-dimensional hexagonal closed pack layers. The 3-dimensional hexagonal closed pack structure can be obtained by placing 2-dimensional hexagonal structures one layer above the other. Placing second layer over the first layer. Let us take a 2-dimensional hexagonal closed packed layer A. Notice this layer has triangular voids. Place a similar closed packed layer in such a way that the spheres of the second layer are placed in depressions of the first layer. As the spheres of the second layer are aligned differently as compared to the first layer, so let us call this layer as B-type. On observing, we will notice that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to a different arrangement and different voids. Voids. There are 2 types of voids: tetrahedron voids, denoted by T, octahedron voids, denoted by O. Let us study how these voids are formed. When we place a closed packed layer above the depressions of the first layer, we will notice that at some places, the triangular voids of the first layer are being covered by the spheres of second layer. At such places, a type of void is formed. This type of void is known as tetrahedral void, T, since a tetrahedron is formed by joining the centers of the 4 surrounding spheres. While at other places, we will notice that the triangular voids of the first layer coincides with the triangular voids of the second layer, such that their triangular shapes do not overlap. At such places, another type of void is formed. This type of void is known as octahedral void, O, since an octahedron is formed by joining the centers of the 6 surrounding spheres. Now, in case we need to calculate the number of tetrahedral and octahedral voids in a crystal structure, then just knowing the number of spheres will serve the purpose. Suppose there are n spheres in the crystal structure, then the number of octahedral voids generated is equal to n. The number of tetrahedral voids generated is equal to 2n. Placing third layer over second layer. Now let us place third layer over second layer. Stacking of third layer over second layer can be done in 2 ways. First, by covering tetrahedral voids. Second, by covering octahedral voids. By covering tetrahedral voids. The tetrahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer will get exactly aligned with the spheres of the first layer. So, if we can call the first layer as A-type and the second layer as B-type, then the third layer will also be A-type. As the pattern of spheres is repeated alternately in other layers, so this pattern is known as AB-AB pattern, and the structure formed is known as hexagonal close packed HCP structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12. Covering octahedral voids. The octahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer are not aligned with the spheres of either first layer or second layer. So, if we call the first layer as A-type and the second layer as B-type, then this third layer will be C-type. Now, if we place the fourth layer over the octahedral voids of the third layer, then the sphere gets aligned with the spheres of the first layer. Thus, this pattern is known as ABC type, and the structure formed is known as cubic close-packed CCP or face-centered cubic FCC structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So, the coordination number is 12.
Alrighty. Nice video, right? I know I'm still in a small window. So this is the channel, okay? you can see over here Scholars Wing. Yeah, so huge shout out to Scholars Wing channel for creating this amazing video. And it's very difficult to explain solid state without such a video, so hats off to them. I just hope that they don't put a copyright strike on this video. But yeah, for the live class at least you got to see the entire animation. Yeah, so in this animation we've learned a lot of interesting things. Yep. In the animation, we've learned a lot of interesting things, isn't it? And the animation allows us to visualize all of these things much better, right, people? So, are you alive? If you're alive, please write alive in the chat box so that I know that you aren't gone. Okay. So, what that video showed us was how these hexagonal closed pack layers can be placed on top of each other, right? How these hexagonal closed pack layers can be placed on top of each other. And what we notice now are these gaps between these layers. These gaps between the layers are very important. These gaps between the layers are called voids. And now let's start shifting our attention towards voids. Let's understand the different types of voids that are present. And we'll talk about them eventually. Okay. So let me go to a blank page. इसमें थोड़ी voids की discussion करते हैं. So let's come to just the two-dimensional packing. Okay. And this is something that we all can draw. So please try to draw with me in your notebooks. So in two-dimensional packing, what was there? In square packing, something like this was going on. Yeah. Square packing में something like this is going on. Okay. Square or sphere on top of sphere. Yeah. Now we have hexagonal closed packing in 2 dimensions. Let's make that one also. I know this is a little lengthy, a little boring at some points, but it takes time, so it takes time. Can't do much about it. If the JEE paper was interesting, then all 10-20 lakh people who take JEE examination, they will all be in IIT. So there has to be some boring part. Now over here, my dear friends, do you notice this particular gap? Do you notice this gap over here? Yeah. This gap basically is known as my void. Okay. Do you notice this gap over here, this triangular gap over here, this tiny little triangle? Okay. This gap is basically a void. Fine. Now in 2 dimensions, this particular void, if I'm very imaginative, I can see a square over here, isn't it? Just in 2 dimensions, I can see a square over here. So I can call it a square void. This is just for 2 dimensions, okay? In 3 dimensions, we'll give fancier names. This, my dear friends, this looks like a triangle, but you know in chemistry, we don't say triangle, we say trigonal. Yes. So this particular void can be called a trigonal void because it looks like a triangle. It is surrounded by basically 3 spheres that are touching each other. So this kind of a triangle is formed in the middle, sort of. And this particular void is known as the trigonal void. Fine. So we understood square void, trigonal void. Fine. This is what we have in 2 dimensions. At any point of time you want to pause the video to write things down, you can. Now let us try to do the same things in 3 dimensions. Okay. In 3 dimensions, in square packing, let me go back to the image of square packing because it's easier to show in that image itself. Yeah, over here. Just notice 1 unit cell. Okay, just notice 1 unit cell. So if you want to draw, let's try to draw a unit cell over here. Something like this is going on. Badhiya. And now, my dear friends, what is happening in this particular unit cell is all corners are occupied, simple cubic. So basically the space that is there in the center, basically the space that is there in the center of this cube, this is known as a cubic void. The empty space that will be there in the center of this cube, all the corners are occupied, so the center will be empty, right? So that empty center is known as a cubic void. How many atoms does a cubic void have as immediate neighbors to it? So cubic void is there in the center. Around the cubic void there are 1, 2, 3, 4, 5, 6, 7 and 8 spheres. Yeah. So the cubic void has 8 immediate neighbors. If you were to sit into that void, okay, if you became like small microscopic and you went and sat in that void, around you, you will see 1, 2, 3, 4, 5, 6, 7, 8 atoms. You will have 8 atoms of the solid as your neighbors. This number, immediate neighbors, the immediate neighbors that you can see around you, this is also known as coordination number. Number of nearest neighbors. Got it? Yeah. So in a cubic void, 8 is the coordination number. Very easy to see the cubic void. That's basically the center of this simple cubic unit cell. Yeah. ठीक है ना? बढ़िया. Very nice. Now, just to recap for the 2D voids, okay? In 2D voids, for a square void, people, what is the coordination number? 4. Because basically you just have 4 circles next to each other. So this gap over here has 4 nearest neighbors. It is 2-dimensional. You don't have 3-dimensional. So the coordination number will be 4. What about the trigonal void? Obviously 3 nearest neighbors. Yes, this is the image that we know. This is the void at the middle. So there are 3 nearest neighbors. So coordination number for a trigonal void will be 3. So if you were to go into a trigonal void and sit there, you will have 3 people next to you. Someone is saying essentially the body center? Yes. The body center of a simple cubic unit cell is basically a cubic void. Okay. So, badhiya. Now let's come to the complicated case of hexagonal closed packing. Okay. अब फिर से हम drawing करेंगे. Okay. And this is almost the last piece of fancy drawing that we have to do. ये focus कहाँ चला गया बे? आजा भैया. हाँ, आ गया. Focus infinity में चला जाता है वो. Stuti, so I've kept the brightness lesser because of the things that I'm writing on the screen. I know my face looks very weird in this bad brightness, but it is what it is, man. Don't worry, now that I'm back here, I will improve the studios. I will definitely make sure that the studios become better. Right now, there are lots of things here and there in the studios. Anyway, so people, let's do the drawing once again. Badhiya. One hexagonal layer, and then we'll make the 3-dimensional layer as well. Fine. Now what we'll do is we'll place the next layer in the trigonal voids of the first layer. These are my trigonal voids. Let's take the upward pointing trigonal voids. So let's put spheres on the upward pointing trigonal voids. So it will look something like this. Hanaji, again over here I have to cover the upward pointing trigonal voids. क्या गजब ड्राइंग करता हूँ भाई मैं कभी कभी. Looks very pathetic, but fine. So this image, let me just show you the one that we have drawn already over here. Drawing it again and again so that you also have time to draw it in your notebook. Okay, so this class might seem slow, might seem boring, but I've seen people get very confused in these topics, so I'm taking a lot of time to explain things. So if it's boring, I'm sorry, but I hope you understand that there's a point to it. Chalo. So now, my dear friends, when we do that, there's a base layer and there's a top layer over here. When we put the base layer and top layer together, we now get two different types of gaps in 3 dimensions. One such gap is the one represented with a T over here, yeah, this particular gap. And one such gap is represented by the O. Now, you saw in the animation how these two are different from each other. Let me try to show you another view of these particular voids, okay? This is what a specific T void or a tetrahedral void looks like. A tetrahedral void is basically the gap that is formed when 3 spheres at the bottom, a trigonal void at the bottom is covered by a sphere. Do you realize? At the back there is a trigonal void. On the trigonal void, if you place a sphere, you get a tetrahedral void. Okay, ji? If you want to draw it, let's draw that. You draw a trigonal void, and on top of the trigonal void, you place a sphere. So this now gives me a tetrahedral void. Now this tetrahedral void basically has 4 nearest neighbors. This tetrahedral void has 1 sphere on top and 3 spheres at the bottom. Can you see 1 sphere on the top, 3 spheres at the bottom, 1 sphere at the top, 3 spheres at the bottom? You're putting this sphere on top of the void. Yeah. This is what the shape of the void will look like. Like we do triangle, square, cube for the 3D, for the 2D and 3D voids earlier. Over here, if we draw the shape, it'll look like this. This is a tetrahedron, basically a pyramid. Yeah. This is what the shape looks like. And over here, this tiny little void is basically has 1, 2, 3 and 4 nearest neighbors. Okay, so the coordination number for this guy becomes 4. If you have studied organic chemistry, do you remember the shape of carbon is tetrahedron or CH4 shape? You remember in hybridization? In hybridization, we have done CH4. Yeah, sp3 hybridization example. So what does this carbon look like? This carbon basically looks something like this. Yeah, I'm sure you have seen this particular drawing of carbon in chemical bonding once, and maybe if you are studying organic chemistry, you've seen this a lot. Carbon surrounded by 4 hydrogens at 109.5 degree angles. So this, my dear friends, is what? This shape is a tetrahedron, yes? This particular shape that we have is a tetrahedron. This shape, same shape for the void. So you can imagine this guy that hydrogens are the solid atoms and carbon is sitting inside the void. Just for imagination. Okay. नोवा देखो सारी शेप्स जो मैंने NCERT से ली हैं, but I will take a PDF and try to upload it on the Telegram group. Okay. क्लास के एंड में याद करा देना मुझे. Okay. Tetrahedral void. Now the next case is octahedral void. What we are doing is basically we are taking a trigonal void and putting another trigonal void on top of it. Can you see? If you want to draw that, you take a 2-dimensional trigonal void and place another trigonal void on top of that. ठीक है, इसके ऊपर एक और trigonal void रख दो. Cool. When this occurrence happens, the gap that we have in the middle has 6 nearest neighbors. Yes? 3 on top and 3 at the bottom. Like this. 1, 2, 3, 4, 5, and 6. So the coordination number over here becomes 6. Octahedral void. Tetrahedral void, because the shape that you form out of the tetrahedron, out of the void, is tetrahedron, and over here you will have an octahedron being formed. 3 atoms at the top and 3 atoms at the bottom, and you're sitting in the middle. Octahedral void. Okay, so tetrahedral void was formed when you take a 2-dimensional trigonal void, place a sphere on top of the void. Octahedral void was formed when you take a 2-dimensional trigonal void and place another trigonal void on top of it. Very nice. Now, people, with the help of our pathetic drawing that we did again and again and again, plus with the NCERT images, plus with the video that I showed you, plus again with these drawings and images, is it clear what these voids look like? Yes or no? Is it clear what these voids look like? After all this mumbo jumbo, I'm sure now you're like, okay. Now it makes sense. Right? Generally what happens is when you teach this type of topic in an offline class, it's not easy to show any animation. Kuch bhi nahi, matlab you'll have a whiteboard or blackboard, you keep drawing on it. It's very difficult. Yeah. If you have a modern day classroom with this type of a screen, then you can maybe show some videos on this screen. So yeah, that's nice that you can do. So this is the benefit of teaching on YouTube, that I can show you videos and get things done easier. Fine. This is done. Voids. So just to revise our voids that we've done till now, okay? Voids थोड़ी सी revise करते हैं. As soon as I stop drawing on the board, then this camera loses focus. It focuses into infinity. Basically, it thinks that this is empty space. Chalo, theek hai. So let's just revise the voids that we've studied till now. Okay. Aaja mere bhai. Cool. So first let's revise the 2-dimensional voids. You had a trigonal void. Then you had the square void. Then let's come to 3D. 3D mein the simplest one to understand was the cubic void. And then we had the tetrahedral void. And then finally we had the octahedral void. Fine. Trigonal voids are found in 2-dimensional hexagonal packing. Yeah. This is found in 2-dimensional hexagonal packing. So instead of saying hexagonal packing, square packing, I can use abbreviations. HCP is equal to hexagonal closed packing. Obviously, I'm sure you know this already. And CCP is basically your cubic closed packing. Fine. So trigonal basically comes from an HCP kind of packing. Square comes from a cubic kind of packing. Square packing, but you can call it a 2-dimensional cube, right? So this comes from HCP, this comes from CCP. What's the coordination number of the trigonal void? 3. Coordination number of the square void? 4. Now cubic comes from cubic closed packing. Tetrahedral again comes from hexagonal closed packing. And octahedral again comes from hexagonal closed packing. Coordination number 8. Coordination number 4. Coordination number 6. Sorted. In your notebooks, if you want to draw, you can draw the shapes as well. Triangle की ये shape बना लो, स्क्वायर की ये शेप बना लो, क्यूबिक में क्यूब बना लो, टेट्राहेड्रल में ट्रायगोनल void and a sphere on top, octahedral में trigonal void and another trigonal void on top, something like that. Done. Voids, everyone understands these now. We already know where a cubic void is present, in the center of the simple cubic unit cell. Now the question is, where are tetrahedral and octahedral voids present? Where? Now that is the question. Where are my tetrahedral voids present? Where are my octahedral voids present? That is what we'll understand today, and then we will end the class eventually. ये समझ लेते हैं पहले. So people, in the hexagonal system as well, as you saw in the video, there can be two types of packing. There could either be AB type of packing, yeah, AB type of packing, and you could also have ABC type of packing of hexagonal layers. Yeah. Now both of these give rise to two different kinds of unit cells. Both of these give rise to two different type of unit cells. Okay, these are the two. One cases of AB kind of packing you can very easily see over here. It forms a very nice hexagonal structure, right? Yeah, can you see? If I just take this much, can you see this unit cell being formed? Yeah. Of the bottom layer A, these are the atoms. Of the top layer A, these are the atoms. And the middle layer B, these are the atoms. This is the unit cell that forms out of this type of a lattice. Only the relevant atoms have been shown. The entire layers have not been shown over here because then it will be difficult to visualize. Fine. So AB, hexagonal packing. If you keep repeating this, the unit cell that comes out of this type of arrangement is the hexagonal unit cell. HCP, hexagonal closed packing unit cell. Okay. Now on the other hand, if you arrange ABC out of a hexagonal closed packing, surprisingly, you get a cubic unit cell. Hey, what the? Sir, you were saying that we have hexagonal packing on hexagonal packing on hexagonal packing, A, B, C, A, B, C, and ultimately out of all these hexagons, you're giving us a cube. ये क्या हो गया? Where did this cube come from? Which cube is this? Can you notice? Atoms at all corners and atoms at all face centers. Yeah? All the blue ones that I've tick marked are face centers. All the corners. पंजाबी में बोलेंगे तो आ कित्थों आ गया? Where did this come from? Let me try to show you a better image. ये देखो. Again, shout out to chemzipper.com. ABC kind of packing is going on. I have taken only the relevant atoms. ठीक है? AB इसको भूल जाओ. हाँ, sorry. This is the pattern. ABC. Yeah. Out of these, I take only the relevant atoms. ABCA. One each from the layer A. From layer B, I have 6. From layer C, I also have 6. ठीक है? And then notice the arrow. This is one way to see it. What is CCP? CCP is cubic closed packing. Basically, if you have a hexagonal closed packing of ABC type, if you look at it like this, it looks like a cubic closed packing with FCC, यानी कि face centered cubic unit cell. This is one way to visualize it, okay? You take these atoms from the ABC layers, tilt it, this is what you get. Looks like FCC. Okay. एक और image देख लेते हैं. This looks even better. ABCA. Turn this arrangement 45 degrees, you get this. And this, my dear friends, is a perfect face-centered cubic unit cell. All we have done is we have changed the perspective of looking at the lattice. You were looking at it at this, oh, hexagon, very nice. Someone comes and be like, bhai, aise dekh. Tilt your head by 45 degrees, now see. Oh, it is cubic. I can see FCC in there. Okay. All the atoms have been shown where these are. Yeah. So these are my corner atoms. And the rest are your face centers. Cool. बढ़िया. कितना कुछ ही कर लिया अपन ने. Okay. We've done so many things now. Next thing that we will do is read a little bit about voids, and then finally we will revise all the things that we've done till now. कितना time हो गया live stream को? 1 hour 3 minutes. चलो ठीक है. We still have some time. Solid state classes are long. So voids में क्या लिखा है? Even in the most efficient packing, be it cubic closed packing or hexagonal closed packing, both of their efficiencies are 74%. We have already derived this for FCC in the previous class, okay? 74% packing efficiency, we have derived this for the face-centered cubic unit cell in the previous class. For hexagonal closed packed unit cell, the hexagonal unit cell that we saw today, the packing efficiency is 74%. Just remember it for now. How to calculate it? It's very difficult. There was a JEE Advanced subjective level question in way back when JEE Advanced used to be subjective. So then they had asked a very nice question of calculating the packing efficiency of HCP on paper. So it's a little difficult to do, but maybe later on by the end of this chapter, if we have some time, we'll do that. Okay. But for now, just try to remember it that for cubic closed packing, that gives you an FCC unit cell, or hexagonal closed packing, that gives you a hexagonal unit cell. Both of them are very efficient at packing. Because you saw, right, we are just putting hexagonal layers on top of each other. Obviously, they're going to be very efficiently packed. 74% packing efficiency. But again, there is some empty space. You can become a microscopic version of yourself and go sit there if you want. So rest of the space is empty, and this empty space is called a void. Now, the size of the void can be expressed in terms of radius ratios, that is small r by capital R. R is the radius of the surrounding sphere. Small r is the radius of the sphere that can actually fit in the void. Now, a lot of you might be thinking, who are new to this chapter, that, sir, what? Why do we need to think about the space of the voids? Like, we've already made the solid lattice, right? So what do we do with the space in the voids? My dear friends, think about it like this, okay? Let's say you have NaCl. Let's say you have NaCl. Now what will happen in NaCl is chlorine will occupy the main lattice points. Chlorine will occupy the corners, chlorine will occupy the face centers, and then whatever gaps are remaining inside the face centered cubic unit cell, sodium will go and sit in those small spaces. Yeah? So whenever we think about ionic solids, one of the ions is a bigger sphere, one of the ions is a smaller sphere. The bigger ion will take up the main lattice point. It will create the basic lattice. So for example, chlorine creates the basic cubic closed packing lattice. Okay. Now whatever gaps are there in the middle, sodium, the smaller ion, just goes and sits over there. And that is why understanding voids is important for us, because different ionic compounds will have different radius ratios. Na positive ratio, Na positive radius divided by Cl negative radius, that's a certain radius ratio. If we have a different type of ionic compound, let's say zinc sulfide, ZnS, Then zinc to positive will have a certain radius. Sulfur to negative will have a certain radius. Divide those radii with each other, you'll get a certain ratio. Yeah. So, depending on the sizes of these ions that come together, they will form different types of packing systems, occupying different kinds of voids. Yes. So that is why understanding these voids are important. Fine. So R is the radius of the bigger sphere. Small r is the radius that can fit inside the void. There are various types of void depending on the size and number of spheres, which we've already seen. Okay. Fine. So what I want you to do right now, okay, right now with me, I want you to do just one analysis and then we'll finish today's class. This class will be continued later, most likely on Monday. So I want you to figure out the radius ratio. अरे भैया ये तारों में गिर के फंस जाऊंगा मैं किसी दिन. So I want you to figure out the radius ratio for a trigonal void. Let's make a bigger image. I'll tell you why. Oh. Fine. Can you see in the middle we have a two-dimensional trigonal void? Now let's imagine that we have to fit another sphere inside the trigonal void. Why? Because atoms are spheres, ions are spheres. If these are bigger ions, a smaller ion has to go and fit inside this void, yes? That will also be a sphere. So let's say that there is a sphere inside this, okay? For two dimension, you can think of them as circles, right? Now, my dear friends, I'll do some geometry with you. We'll do some geometry, some trigonometry over here. Take the midpoint of one of these circles. How much is this distance? From the midpoint to the edge of one circle, this is the big radius r. Now, my dear friends, can you see how much is this line equal to? From the midpoint of the big sphere to the midpoint of the small sphere, how much is this line equal to? My dear friends, if you have enough, if you have eyes, I'm sure you can see that this is equal to big R plus small r. This is the big R, this is the small r. Yes, big R, small r, big R, small r. So this is big R plus small r. Also, people, I'm sure you know from childhood, this is an equilateral triangle. This is what? 60 degrees. So what is this angle? This will be the bisector, right? Equilateral triangle, everything is symmetrical. So this angle over here, my dear friends, is 30 degrees. Yes. इतना तो चमक गया आपको. That this angle over here is 30 degrees. Now, can I write a relationship between r plus r and r? This is what the hypotenuse. This is what base calo, adjacent calo, depending on what angle you're looking at. Okay. Depending on what angle you're looking at, you can call it the base, you can call it the adjacent. But since we're looking at this angle, let's call it the adjacent. Okay. So I can write a cos theta relationship over here, isn't it? That r plus r into cos of 30 degrees will be equal to समझ में absolutely correct. Cos theta लिख दिया ना अपन ने यहाँ पे. Fine. This is what I can write. Or I can write cos of 30 degree is equal to r by r plus r. या इसको उल्टा लिखना तो you can write something like r plus r by r is equal to 1 by cos 30 degrees. People, what's the value of cos 30? Cos 30 कितना होता है? Tell me. Samanyu, linear void will be a case where there are two spheres with a gap between them and there's a smaller sphere sitting over here. So this is a linear void. Okay. So for example, you have BeCl2, right? Linear. So can you imagine that chlorines will be bigger spheres, beryllium is smaller spheres. So this can be thought of as a linear void. Okay. रूट 3/2, ठीक है. तो इसको कैसे लिख देंगे? 2/√3. I can simplify this as well by writing it as 1 plus small r by big R. So finally, my dear friends, this small r by big R is my radius ratio. Fine. So this small r by big R is equal to how much? 2/√3 minus, sorry, this will be 1 minus 2/√3. Yes. If I have done anything wrong, please let me know, okay? फिर कुछ गड़बड़ की मैंने, है ना? क्या कर रहा हूँ मैं? Yeah. Can you guys give me the answer to this? ये कितना आ रहा है? Can you tell me what is the answer over here? 2/√3 minus 1. बताओ बताओ बताओ. Someone you already knows. Someone who has done the calculation, people. 0.155. Yes. आ गया ये. So essentially, the radius of the smaller sphere over here is only 0.155 times the radius of the bigger sphere. The radius ratio of a trigonal void is 0.155. What does this mean? The English statement, the last statement of today's class. If there is a sphere that sits perfectly inside a trigonal void, if there is a circle, talking about 2 dimensions, if there is a circle that fits perfectly in a trigonal void, the radius of that circle will be equal to 0.155 times the radius of the bigger circles. Yes? Understood? I'll repeat the statement in Hindi as well, for those of you who understand better in Hindi. अगर अपने पास एक ट्रायगोनल वॉइड है और उस ट्रायगोनल वॉइड में अपने को एक स्फेयर बिल्कुल परफेक्टली फिट करना है विदाउट एनी गैप्स, ओके, इस स्फेयर को भी, इस स्फेयर को भी, तीनों स्फेयर को टच कर रहा है ना, परफेक्टली एकदम फिट करना है वहां पे, तो इस छोटे सर्कल का जो रेडियस होगा वो 1.15 टाइम्स होगा बड़े स्फेयर के. ओके, बड़े स्फेयर के रेडियस को अगर आप 0.155 करोगे तो छोटे स्फेयर का रेडियस आ जाएगा. रेडियस रेशो, right? Simple. So this is the radius ratio of the trigonal void. Now, my dear friends, in the upcoming classes, we will do the radius ratios of tetrahedral void, octahedral void, how to see that, where are those voids present in different unit cells, and then, given these radius ratios, what are the different real ionic solids that can, be placed in these different unit cells. So for example, where can I place chlorine negative? Where can I place sodium? Where can I place cesium and chlorine in cesium chloride, let's say? Where can I place zinc and where can I place sulfur in zinc sulfide, etc., etc. So that is the analysis that we will do in the upcoming classes. Most likely the next class will be on Monday, but we are planning some more things as well. So don't worry, I will do these classes. Just stay subscribed and I'll complete this chapter for you for sure. Yeah, trigonal void अपने पास हो गया. We've calculated the radius ratio of the trigonal void, and this is all that we'll do in the next class. Okay, we'll look at the FCC once again, radius ratio of the tetrahedral void, so on and so forth. Fine, people. So I have one piece of homework for you. The one piece of homework that I have for you for today's class is read the NCRT. As simple as that. Okay. Samanyu, okay man. Suggestion taken. Definitely for the droppers, I can take a strategy session very soon. Coordination chemistry, I'll have to study it myself. It's been a very long time I've studied coordination properly, but I'll try to take a session on. I'll try to complete that chapter as well. Fine. So people, only one homework for today. Read the NCERT of this chapter entirely. छोटा सा लिखा हुआ है chapter NCERT में. Whatever I told you today in the entire 1 hour 15 minutes type of class. In NCERT, it's given in 3 pages. NCERT is very efficiently written. So read the NCERT, you will automatically revise the class. That's the homework. And with that, I'm going to call it a day. Thank you so much for joining in, people. I hope you're enjoying these lengthy classes with me. If you are, make sure you hit that thumbs up button. Stay subscribed to the channel. If you are willing to share it with some friend of yours, please do so. Because if this channel grows bigger, it's your advantage and my advantage at the same time. So yeah, thank you so much for joining in. Stuti Organic 12th, I haven't planned yet, but I will plan very soon. See, the thing is that Pulkit sir and I are planning to do things now in both English and Hindi. Essentially, we want to teach students in both languages, yeah, because we know both languages pretty well. So English ka you've seen all that we are doing, and we are trying to get to the proper schedule of things. And now we have to do some things for Hindi as well. So we're still not sure exactly how we'll do these two things together, but slowly and steadily we're starting. So that's why you'll see us doing classes in Hindi as well, not on Catalysis, on a different channel, but you will see that very soon. Okay. So slowly and steadily, I think in the span of another month, we will get into a flow. But during this month, we will definitely keep teaching you. We'll definitely keep giving you question of the day, etc., etc. उस चीज़ की tension लेने की ज़रूरत नहीं है. Fine. चलो दोस्तों, that's it from my side. Thank you so much for joining in. Good night, and I will see you later whenever I get to see you again. Bye bye. Samanyu will do beatboxing in some live chat session, because right now my throat is gone after speaking for 2.5 hours. Chalo ji, bye bye. Thank you so much. Good night.